Today we're going to create a system for efficiently finding objects in 3D space using spatial hashing. This is a technique used to efficiently partition 3D space into a grid of discrete cells, and it allows fast lookup and querying of objects based on their positions by mapping them to specific grid cells using a hash function. Using this technique means we don't have to query the entire space to find the objects that we're looking for. And not just that, but we're going to use jobs and bursts today so that we can efficiently find thousands of objects every frame. We'll demonstrate this by finding every object that falls into a certain area of the grid every frame and update their colors to red. Let's get into it. I'm going to expose a few properties to the editor here. I've already created a prefab for the particles, which is just a little sphere with a black material. We'll have a count, how many particles we want to have actually moving in the area. Let's also have a bound struct that'll define the area the particles can move in. I might want to change the max radius of these spheres. And the cell size. This will be how small we want to divide up the 3D space into. Now, within this 3D space where the particles are flying around, we're going to want to query a specific area. In today's example, we're going to use a sphere, and we'll just reference that by its transform. And we're going to want to be able to change its radius at runtime. So let's expose a float for that as well. And finally, I've set up a small UI just so we can use sliders and toggles for all these things. So I'll just add some boxes here so I can drag in the references. So I've got a slider that will allow us to change how many particles there are, and another one for dividing up the 3D space, and a third one for changing the size of the query area. I'll also add a field so we can output some text about our results. And finally, I'll just have a little toggle that'll allow us to turn gizmos on and off, and we can store the result of that toggle in a little boolean here. For the actual query area, I'm going to create the visual using code, but I am going to get a reference to a semi-opaque material from Unity. So with all that setup done, I think we can collapse up these dependencies and all of these settings and references and give ourselves some space. The next thing to do is inside of the start method, let's hook up our UI elements to do different things. I want the particles slider value to be the same value as our actual count that we've set inside this component. But whenever that value changes, I want to make sure that we've spawned the right amount of particles. Let's create a separate method for that. Whenever I click on the grid toggle, I want to just flip that Boolean's value. Then I have another slider that defines the actual size of the grid. Let's do the same thing here. Make sure it starts at the right value. But whenever I change it, I want to make sure that our cell size actually gets updated as well. We can hook up the slider for the query radius in exactly the same manner. And when that's done, I want to run initialize particles for the very first time. Now, the first thing to do when we're spawning the particles is to make sure that we're working with an integer value. And we're going to need to store them somewhere. So right here, let's define an array of game objects that we can stash them in. But let's also have an array of renderers because I don't want to get component all the time. And I want to change their colors as they come in and out of our query area. Now, anytime we come into this method, it means that we've changed the number of particles that exist. If we've already created some particles, let's loop over the ones that do exist and destroy them all. Now we've got a clean slate. So let's initialize the two arrays from earlier. And I'm just going to hit page down here to give some room. Now here we can run a for loop over the actual number of particles that we want to be spawning. For each one, I'm going to choose a random position where the X, Y, and Z fall within the particle bounds area. Then we can give it a random radius that falls between something small like 0.5 and whatever the max radius was that I set in the inspector. And then we can actually instantiate one of these prefabs at that position. Let's make sure that its size is exactly vector 3.1 multiplied by the radius, multiplied by 2, of course. And then to keep our hierarchy from overflowing, let's actually parent that under this game object. Okay, I think we're set up pretty nice for a simulation. Let's have a sanity check really quick. Okay, well, I've already connected up all my references and my UI elements. If we click play, we should see 500 black spheres spawn right in this area. Good enough. Well, how about we start using the job system to move them around? To pass in information about each one of these sphere particles, I'm going to create a new struct here. We'll need to pass in information about its position, velocity, and radius. We're going to store all of those in a native array. A normal array uses managed memory to allocate on the heap. On the other hand, a native array gives us direct access to native memory outside of the managed environment. This results in faster performance, especially for tasks like physics, rendering, or anything that's multi-threaded. That also means it's not managed by the garbage collection system. So when we're finished using this memory, we need to release it using the dispose method. You never want to call dispose on an array that was never initialized because Unity will throw an exception. This is because the native array is in an uninitialized state and there is no allocated native memory to release. So before calling the dispose method, it's a good practice to check the isCreated property. So let's come down a little bit. Where we're initializing the other arrays, let's also initialize our native array. I'm going to pass in allocator.persistent. This is useful if you need a native array to last for multiple frames. There are other types of allocator settings you can use for just one frame or just a few frames, but persistent is for a longer period of time. Where we're creating our other settings here, let's also add a velocity. We'll just pick a random vector 3 for that. And that's all the settings we need. So at position I inside of the native array, let's create a new particle with the position, radius, and velocity. Now in our regular arrays, we should also stash our instance, and I want to stash that renderer as well. Okay, well, let's zoom out here and we could probably collapse up a few things before we start writing our very first job. We're going to be firing off the job inside of the update method. And the very first thing I'm going to do here is have a guard clause. If we haven't initialized our native array, let's just bail out of here. Now we actually need to create a job to run here. So let's define a new struct. We'll call it update particles job. A job can't be a class and it can't accept parameters that are references because classes and reference types are stored on the heap. That violates the job system's requirements for blittable value type data that ensures thread safety and efficient memory access. Now, blittable refers to types that have a direct memory representation and can be copied without any transformation between managed and unmanaged memory. That means the memory layout is fixed and it doesn't require marshalling, making them safe for performance-critical operations. Examples of blittable types are primitives like int and float, and structs that contain only blittable fields like the particle struct we defined earlier. So let's have our job implement the iJobParallel4 interface. Now this interface defines a multi-threaded job that will run in parallel across multiple elements of an array or collection. It has one main method, execute, which takes in an index of the array or collection you're working on. Beyond that, I'm going to add the burst compile attribute here so that we make sure that we compile this job into efficient platform-specific machine code. So this first job is just about moving particles around. It's going to need a native array of all those particles. It's going to need to know what the min and max of our bounds are. I'm also going to pass in delta time. Then in the execute method, let's grab out the particle that's at that index. Then we'll adjust its position by its velocity multiplied by delta time. Now it's possible as we're adjusting the position here that we could go out of bounds. So let's make it bounce off the bounds instead. If we hit the min or the max of the bounds in the x direction, let's just flip our velocity. Let's do the same for y and for z. At the end of this, we'll just make sure that we assign that particle back into the native array at our index. So let's collapse up this job that we just wrote, and we're going to come back into the update method and actually fire it off. So let's create a new update particles job here, and we can initialize it with our native array, our particle bounds min and max, and we'll pass in delta time. We can run this job by using the schedule method. I'm going to pass in 64 here, and that represents the batch size. That's how many iterations of the job each worker thread processes at a time. We can store the running job in a job handle, and before we access the results, we need to call complete. That makes sure that it's fully finished executing before we access the results and move on to any other operations. Now the results have all the updated positions, so let's iterate over our particles and update all of their positions using these new calculated values. And that's it. All of the particles will get a new position every frame. Just one more thing to do. I want to make sure that we properly dispose of this native memory. So let's add an onDestroy in here. Let's just check is created. And if it is, let's dispose. Okay, hot reload did its thing. All we have to do is hit play. And sure enough, we have hundreds of black spheres moving around within the bounds, and they're all at different velocities and sizes and bouncing off the edges. So far, it looks pretty smooth, right? What if we crank it up to several thousand? Let's see how that looks. I'll just adjust the slider up a little bit here. There we go. That should be about 2,000 maybe. So zoom out. Actually looks kind of cool. Now that this is all working nicely, we can set up our spatial hash. To create the spatial hash, we're going to split up our bounds area into smaller cubes. Each of these smaller sections of our 3D space will be identified by a hash, and it can contain 0 or more particles. So we're going to create a struct here that will associate a hash with an index from our array of particles. I'm going to implement iComparable here because I want to be able to quickly tell if a particle at any given index is in the same hash as another one. So we'll just compare hash values. To create these hash values for the smaller cubes of our 3D space, let's have a new static method here. It'll take in an int3 grid position. I'm going to multiply the x, the y, and the z all by large prime numbers, and I'm going to combine them with bitwise XOR. I'm going to wrap it in an unchecked block so that it can overflow without throwing an exception. And we'll be able to use this as our identifier for all of the small subdivisions of our space. Okay, so now we can ID all the subdivisions and we can associate particles with each of the subdivisions. Let's page down to the bottom of the class. We're going to create a new job that will associate each particle with one of these subdivisions of our space. Let's set up a hashed particles job marked as burst compile and implementing iJob parallel 4. It's going to need all of the particles. I'm going to mark it as read-only, even though that's not strictly necessary for what we're doing today. But marking something as read-only would mean that 2 jobs running in parallel could both safely read from this particular array. A native array behaves like a pointer to the underlying native memory, which holds the actual data. So when you pass a native array to multiple jobs, you're passing a copy of the reference to the same underlying data buffer. The data itself is not duplicated. Okay, moving on, we're going to need to know a cell size so that we know how small we're going to subdivide our space into. And we're also going to need a native array of the type hash and index so that we can associate all of our particles with one of these small spaces. The first thing we can do inside of execute is grab out one of those particles from the native array. Next, let's create a helper method here that will divide a position in the world by the cell size. Then we can use math.floor and convert it into a new int3 that'll give us a discrete grid cell that the world position falls into. Now, using this helper method, we can get a grid position for this particular particle, and then we can pass that grid position into our hash method to give us that unique hash. Now we've got everything we need. We can assign a new hash and index into our native array, and we can populate it with the hash and the index. In fact, we could probably skip using that int3 and just inline this grid position right into the hash method here. There we go. So now we've got our hashing method ready. We've split up our 3D space into all these smaller chunks and associated all of our particles with the smaller chunks. But we're going to have to come back up to our update method and actually run the job. But first, let's jump all the way up to the top of the class, and I'm going to define a new native array just for these hash and index values. Then let's come down to our initialize particles method here. Let's make sure that we dispose of that array before we start doing any of the operations that follow. And below, where we're initializing our particles native array, let's also initialize our hash and indices native array as well. Let's collapse up this method and come into update. So down here in the update method, we were calling complete on our last job handle. I'm going to comment that out. Instead, what we're going to do is create a new job here, our hash and particles job. Let's pass in all the data we need, which is our particles native array, the cell size, and our hash and indices array. Now, when I go to run this job, I'm going to call the schedule method, but I'm also going to pass in the previous job handle. That's going to make sure that the previous job finishes running before this job starts running. Then I can now call complete on the second job. Okay, so that will make sure that our 3D space is all subdivided and all of our particles are sorted into those subdivisions. Let's make use of this information by actually starting to query to find out if particles land within a certain area. So now we've essentially bucketed all of the particles into smaller subsections of our 3D world. Before we do anything else though, let's come down into onDestroy, make sure that we dispose of that new native array we started using. Now I'm going to jump down to the bottom of our class here where we were defining our jobs. We're going to create 2 more jobs. The first one is going to be very simple. I just want to sort that entire array. Now, because it's going to be a sort, I'm not going to do the iJob parallel 4. Instead, we'll just run it on one thread using iJob. It's going to take all of our hash and index values, and in the execute method, we'll just run the sort method on that native array. Let's jump back up to our update method and make sure that we're running this job next. I'll comment out our complete. We don't need that anymore because we're going to create a new sort job here where we just pass in the hash and indices array. And here we can run this again. We'll save a reference to this as a sort job handle, but we'll pass in the handle from our previous job. Now we've got one more job to make. Let's come back to the bottom of the class and write that one as well. So the reason that we sorted the values in the previous step is because we're going to do a binary search here. So again, we're going to use the iJob interface, and we'll call this the query job. The query job is going to take values from the particles and from our hash and index array, and we're going to figure out, based on a central position and a radius, whether or not any particles fall into that area. We'll need to know the cell size here as well so that we can correctly calculate hash values. Now, any particles that we do find within the area will store their index values in a native list. That'll be our results. I'll just declare it right above here and I'll move it later to the top of the class. Now, in our execute method, we're going to run our binary search. There's a few ways we could check distance. I'm going to use radius squared. So let's save that value here. Next, let's get the grid bounds of the query area by calculating the min and the max grid positions. This tells us which grid cells need to be checked based on the query position and radius. Now, I already have a grid position method that I put inside of another job. Let's pull it out of that job and make it a static method here. That way all of the jobs can use it. Okay, let's jump back down to the query job and I'll give myself a little bit more space here. What we want to do now is iterate over all the grid cells that fall within the query bounds. So let's have some nested for loops so that we get the X, the Y, and the Z for every single grid cell we're looking through. Now we've got an X, Y, and Z. Let's convert this grid position to a unique hash. Now we can perform a binary search on the hash and indices array to find the first particle with the matching hash. Let's write the binary search before we deal with the results. We're just going to do a standard binary search algorithm here. We need to know a left, a right, and a result which will start at -1. We'll run a while loop while the left is less than or equal to the right. Let's check the value right in the middle. If that hash at that midpoint is the one that we're looking for, then we can say the result equals mid, and we can keep looking into the left to see if there's another value earlier in the array that matches. Otherwise, we can say if mid hash was less than the hash, then we're going to say left equals mid plus 1 because we're only going to look in the right side. And otherwise, we're only going to look on the left side. So we'll set the right value to be mid -1. When we're out of here, we should have our result. Let's return. Now, it's possible that our binary search returned a -1. So if that's the case, we could say if the start index is less than 0, then let's just continue and look in the next grid cell. Otherwise, we know that there's at least one particle in this grid cell. So we can loop through all the particles in this grid cell that have the same hash. Let's get the index of the particle from the hash and indices array. Then we'll retrieve the actual particle data from the particles array using the index. Then we can calculate the vector from the query position to the particle position. After that, we can check if the particle's within the query radius by comparing the squared distances. If the particle's within the radius, we'll add its index to the results list. Okay, now we've written all of our jobs. Let's make sure that we run this one with the others. If we come back into our update method, right after we ran the sort job, let's start another query job. Now the query job needed quite a bit of information. The particles native, the hash and indices native array. It also needed a query position, the query radius. It needed to know the cell size, and it needed somewhere to store the results. Here I'm going to initialize our native list in line. Notice also that I'm going to use allocator.temp job because we don't need this one to persist. Now we can actually run this query job and I'll pass in the previous job's handle. This time we're actually done running all of our jobs. So let's actually call complete on this job. That means that all 4 of our jobs will have run in sequence. Here we've now completed and we can do something with these results. Now I'm going to make a local native list to hold these results. And I'll do that in a minute. But here, let's say that if it was created, let's dispose of it. And then we can populate it with the references that come back from our query job. Now, potentially, we could just use the results that were from the query job as well, since we really only care about it for this frame. Either way, we can now loop over all of our renderers. And let's start by making all of them white. But then we can use our results. And for each of the ones from the results, let's grab it out of the particle renders at that index and set those ones to be red. So the ones that fell within our query will be red, the ones outside will be white. Now, if you did declare a local native list, make sure that you dispose of it in onDestroy. Okay, hot reload and press play, and here we go. So in the middle of our simulation here, you can see a lot of the spheres are turning red and the ones on the outskirts are all white. It's a little bit hard to see though. Why don't we quickly make some gizmos and come back to this? So let's add an onDrawGizmos method right under the start method. I'll make them green, and we can say if the query sphere is not null, let's draw a wire sphere around it. And then we can check our show grid boolean. If that was toggled on, let's actually draw our grid that we've divided our 3D space up into. For that, I'm going to create a new method here. We'll just figure out the grid X count, Y count, and Z count, which is just the particle bounds divided by our cell size. And then we'll have a triple nested loop here, similar to what we were doing down in our job before, but this time we're going to go all the way to the far edges, not just the area that we're searching in. We'll just do a little bit of math to figure out the cell center, and then we'll draw a wire cube around it. But looking at the wire sphere for trying to see where the actual query bounds are is going to be a little bit tricky. Let's have another method here where we actually draw a real sphere. So inside of this method, let's create a new primitive of type sphere. And we can set its parent to be the query sphere transform. And then we can get the renderer and we'll assign a semi-opaque material to it so we can see through, and we'll turn off the collider. Now I need another method here to update the visual because we're going to be able to resize it in real time. So as long as it's not null, let's make sure that it's sized correctly. Now we can run this method from our start method, but we could also run it every update too to make sure if we've moved the slider, our visual stays up to date. So I'll open up start here. Let's add a call here, and then I'll jump down to the update method and we can call that right at the start. Okay, well that should give us some nice visuals to see what's going on, not only with how we've divided up our 3D space, but how we're actually searching for things and finding them within that space. Let's go have a look. All right, well now we've got a nice semi-opaque sphere right in the middle that defines our search area. We can make it bigger or smaller using the slider. As I bring it up to kind of max size here, you can get a real good idea of how the search query is actually working. Any particle that enters into that sphere by its midpoint turns red, and all of the ones that are outside of that range are white. Let's crank up the number of particles and see how it's doing. So that's performing pretty well, and it still looks like it's doing its job. Why don't we toggle the grid? There we go. So you can see here, we've got fairly small grid sizes. That means it's quite accurate, but a little bit more processing. If I were to make the grid cells bigger like this, that would mean there's less cells to check, but there might be more particles inside of them to actually check the distance on. If I were to make them even bigger, you can see now we're at basically a 3x3 grid, and our sphere occupies all of them. That means that we're not really getting any advantage to the system if we make the grid cell size this big. You'd have to check the whole space. So coming down to a smaller size like this, and even if we crank up the particles to halfway, you can see in my text there that I've connected, it's detecting thousands of particles within that system. And we've kind of built in two advantages to this system. First of all, it's not checking every single cube inside of the frame there. It's only checking the ones where the query area is. And the other advantage, of course, is that we're using burst and jobs. So I hope building a little system like this helps explain what spatial hashing is all about and how you can rapidly search for an area in 3D space to find things that match a certain query and even perform logic on them like we're doing here, which is changing the color. Of course, this sort of thing is great for any kind of game where you need to do efficient searching in 3D space for objects. So whether it's an RTS or you've got some big RPG that you're building, or any kind of game where you need to find things in a 3D area, splitting it up like this, just like we did with octrees the other day, is a very efficient way of finding things within a large space. And it works great in 2D, just like it does here for 3D. So I think that's where we'll wrap it up for today. I'll leave this code in a gist, I think, and don't forget to join the Discord. Like and subscribe if you feel so inclined. I'll leave a couple videos linked up on the screen here. Maybe I'll see you there.